So we continue the exercises of kinetic. Multiple choice. Question 15. The activation energy of a certain non-catalyzed reaction is 64 kilojoule per mole. When we add a catalyst, the activation energy will decrease. So the new activation energy is EA equal 55 kilojoule per mole. How many times is the catalyzed reaction faster than the non-catalyzed at the same temperature 400 degrees? Assume that the frequency factor remains the same. So we have to summarize the given. We have two reactions realized at the same temperature 400 degrees. The first is non-catalyzed, no catalyst added. The second is catalyzed. So we realized these two reactions at the same time. We start the chronometer and the kinetic of the reactions start. The catalyzed reaction is faster than the non-catalyzed, since the addition of the catalyst increases the rate of the reaction. And in this problem, they suppose if they change the condition of addition of the catalyst, they suppose that all other conditions are the same. So these two experiments start at the same initial concentration. They ask to compare the catalyzed, the rate of the catalyzed with that of the non-catalyzed. And pay attention, at which time can we compare the rates? When the reaction 1 starts, so the rate of the reaction, suppose, will decrease with time, and the catalyzed starts, the rate decreases with time. We can compare only these two rates at t equals 0, at the starting, since during the reactions, during the kinetic, I could not master the rate to compare the catalyzed and the non-catalyzed. So non-catalyzed, the activation energy is 64, the temperature 400 degrees, and the catalyzed, the activation energy is less at the same temperature. Sure that the reaction 2 is faster than the reaction 1. So R2 should be greater than R1, but now we have to determine the time we want to compare these two reactions. The rate constant of reaction non-catalyzed is different from that catalyzed, since these two reactions are different, even they are at the same temperature. So these reactions are different. K1 equal the frequency factor A E minus EA1 divided by RT1, and K2 equal A E minus EA2 divided by RT2, but the temperature T1 is equal to the temperature T2 is equal to 400 degrees. We assume in this problem that we have the same frequency factor A, since we have the same nature of the reaction. For the same reaction, the frequency factor in your curriculum is assumed the same. So we divided K1 divided by K2. We cancel A. E minus EA1 divided by RT divided by E minus EA2 divided by RT. So len K1 divided by K2 equal len of this expression. So len K1 divided by K2 equal minus EA1 divided by RT minus EA2 divided by RT, so plus EA2 divided by RT. That means len K1 divided by K2 equal 1 over RT EA2 minus 1 over EA2 minus EA1. EA2 is given, EA1 is given, R is given, the temperature is given, so we can compare the rate constant K1 and the rate constant K2. So K1 divided by K2 is equal to 0.2, or K2 divided by K1 equal 1 over 0.2. So K2 divided by K1 equal 5. Till now, the non-catalyzed has a rate constant K1 less than the rate constant of the catalyzed K2, and K1 divided by K2 equals 0.2, or K2 of the reaction catalyzed is greater 5 times K1. The question is not to compare the rate constant. The question is to compare the rate of the reactions. So, since we have the same type of the reaction, so the rate law expression is the form of the rate law expression is the same for the two reactions. The form. When I said the form, I mean the partial orders. So R1 equal K1 times concentration A1 to the power N, R2 equal different rate constant K2 times concentration of A, I will note A2, to the power N, the same partial orders. Since we have the same nature of the reaction, we have the same reactants. So if we suppose in this problem that the initial concentrations we start with in the catalyzed and the non-catalyzed are the same, so we can cancel A1N divided by A2N. At T equals 0, these concentrations are only equal. When the reaction starts, the concentration A1 decrease, the concentration of A2 decrease, but the decrease in A1 is not the same as the decrease in A2, since the two reactions are different. One catalyzed and the second is not catalyzed. So only we can compare A1 and A2 at the T equals 0. So in this problem, how many times is the catalyzed faster than the non-catalyzed at 400 degrees? We should add at T equals 0. We should add at T equals 0. It's not mentioned, so we have to know that we can compare only these two reactions at T equals 0. We cancel A1N, A2N, so we obtain R1 divided by R2 equal K1 divided by K2, and therefore R1 divided by R2 equals 0.2, so R2 equal 5R1. As a conclusion, if you do two experiments of the same nature of the reaction, same initial concentration, but in the second you add catalyst, and you start these two reactions at the same time, at T equals 0, at the starting, the catalyzed reaction is faster 5 times than the non-catalyzed. The question, can we compare the ratio of the rates, for example, after 5 minutes, if we can know the concentration of A after 5 minutes, that of A2 after 5 minutes, so we can compare the rates. But practically, when the two reactions starts, it's not easy to master the concentration of A and B during these two reactions. So at T equals 0, the catalyzed reaction is 5 times faster than the non-catalyzed. The correct answer is A. MCQ exercise 16. Consider a series of reactions having the following energy profiles. Rank the reactions from slowest to fastest, assuming that they have nearly the same frequency factor. So these reactions are realized at conditions, and the variable in these reactions are the activation energy. The activation energy of any reaction is related to the rate constant according to Arrhenius equation, K equal A E minus EA divided by RT. If we suppose that these reactions are realized at the same temperature, I said previously, when we want to study the effect of a certain characteristic, the others should be maintained constant. So in these reactions, we suppose that we have the same temperature. And since the reactions are different, so in general, they should have different steric factor. But in this problem, we assume that they have the same frequency factor, so the same frequency, nearly the same frequency factor. We assume that all have practically steric factor A. So if you observe, since the temperature is constant and A is constant, R is constant, as the activation energy increase, so minus EA divided by RT decrease, so E minus EA divided by RT increase, so the rate constant increase. So the greater the activation energy, the greater the activation energy, the lower K, not the greater, the lower. So as EA increase, K decrease, and therefore the rate of the reaction decrease. So we can compare now the activation energy of the first, of the second, of the third, to note that the activation energy is the difference between the energy of the initial reactant and the top of the variation where we have the activated complex. So the activation energy for the first is 15 kilojoule per mole. For the second, the difference is 25. And for the third, the difference is 20. So EA2 is greater than EA3, greater than EA1. The greater the activation energy, the lower rate of the reaction. So R2 is less than R3, is less than R1, or we can say that the first reaction is the fastest. So the answer is A. Exercise 17. How do you explain the increased rate observed when a reaction is heated? This is the theory of the collision. According to the collision theory, when the temperature increases, the molecules or the particles will absorb energy as kinetic energy. So the molecules will move faster. So we will have more probability of collisions between the molecules of the reactant, and therefore we can have energy greater than the activation energy, so the reaction will start, and as we have more and more collisions, so the rate of the reaction will increase due to the probability of collisions. So when the temperature increase, the rate constant increase. A is correct. The activation energy decrease is incorrect, since the activation energy of a certain reaction depends only on one condition. Do we add catalyst or not? So, a faster pathway can be found. The temperature did not affect the pathway. The pathway is affected only by the addition of the catalyst. So B and C are correct. Till now, A are incorrect, and A is correct. We pass to D. A higher fraction of molecules have enough kinetic energy to have a value greater than the activation energy. This is true. So A and D are correct. Therefore, the correct answer is E. Exercise 18. The decomposition reaction of benzene diazonium chloride in aqueous solution at 20 degrees is a reaction of first order given by this form. Pay attention. The form is not A to product, is A plus B to product, but all integrated rate law can be used as A to product. For the initial concentration 0.01 mole per liter of C6H5Cl, the following kinetic results are obtained. We have time and we have concentration of the product. Calculate the rate constant K and T half. Pay attention. In this problem, we have the variation of the concentration of the products formed as a function of time. And as you know, when we want to study the kinetic, we have to study the variation of the concentration of the reactants per time, and not the product per time. But in this problem, the concentration of the products are given per time. So we can study the rate of formation of H+. If we want to write the rate law expression depends on C6H5Cl H2O and not on the product. So what to do? From H+ formed, we can deduce C6H5Cl reacted, and from C6H5Cl reacted, we can know C6H5Cl remained, since the initial concentration of C6H5Cl is given. So this reaction is of first order. That means ln concentration AT divided by A0 equal minus KT. To calculate K, we have to calculate the concentration of C6H5Cl at a certain time T. Since C6H5Cl 0 is given, so we can calculate K. So knowing the concentration of C6H5Cl at time T, we can calculate K, and then we can deduce T half, since for order 1, T half is equal to 2 over K. So now the objective is to calculate the concentration of C6H5Cl at a time T. According to the given, we have concentration of H+ formed, and the concentration of H+ formed are related to the concentration of C6H5Cl reacted according to the stoichiometry. So C6H5Cl reacted divided by 1 equal H plus form divided by 1. So we can add now a third row where we put the concentration of C6H5Cl reacted. And from C6H5Cl reacted, we can deduce C6H5 remained, since C6H5Cl concentration at time t equals C6H5Cl concentration initial minus C6H5Cl reacted. So the relation we can write C6H5Clt equals C6H5Cl0 minus H plus 4. So we do this table, we complete the table, we add a row where we have C6H5Cl equal initial minus reacted equal the concentration initial 0.01 minus reacted 5.25 10 minus 4, and at 50 equal initial minus reacted at 50 or minus H plus formed at 50. So we obtain the variation of C6H5Cl per time. Now we apply the relation ln AT divided by A0 equal minus KT, which was one of these times. Or you apply the relation at t equal 20 minutes, or you can apply it at 50 minutes. So at t equal 20 minutes, we put the value of AT and A0, so we obtain K, and pay attention, the unit of K is the same as is 1 over time, so it's in minute minus 1. For the first order reaction, T have equal ln 2 over K equal ln 2 over 0.002696. So T have equal 257 minutes. And the answer is B. I pass to exercise 19. Pay attention in this exercise. We will study the integrated rate law as a function of the pressure and not as a function of the concentration. Pay attention for the conditions given. In a constant volume reactor V equal 1 liter, that means the volume is constant. First, we introduce pure ethanol gas that decomposes to methane and carbon monoxide according to the following reaction, and this reaction is homogeneous at the gas state. The reactants and the product are at the gas state. The reaction is second order depending on the initial pressure P0 and Pt. The kinetic law of this order 2 reaction. So we want to study what is the integrated rate law as a function of the pressure and not as a function of the concentration. First, for a reaction of second order, 1 over AT equal 1 over A0 plus KT. So if we replace the concentration by the pressure, we will obtain 1 over pressures equal 1 over pressures plus KT. So look to the proposal, 1 of the pressure minus 1 of the pressure equal plus KT, 1 of the pressure, 1 of the pressure, 1 of the pressure. Suppose in the answers you have ln pressure, you can eliminate directly this probability. You can eliminate directly this answer. So now we have to find what is the variation of the integrated rate law as a function of the initial pressure P0 and the P total PT. First, I will construct the table of conversion. And pay attention, the table of conversion is constructed according to the number of moles. Then, if the volume is constant, we can transform the table of conversion from number of moles to the concentration. So, at T equals 0, I have N0 ethanol, 0, 0 CO. The quantity reacted, X0, we have quantity formed X0, X0. So the quantity remained at T is N0 minus X, or minus X0, plus X, plus X. So X0 and X are the same. Okay, but I use X0 in order to say that we have X reacted from N0. So at time T, N0 minus X, X, X. Can we transform this table of conversion to concentration? Yes, since the volume is constant. So you divide by V, 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 and you transform the number of moles to the concentration. I will add a column. I describe the total number of moles. And the total number of moles is the sum of the number of moles of reactant and the number of moles of product. So at T equals 0, N total equal N0 plus 0 plus 0 equal N0. And at time T, the total number of mole in the reactor equal N0 minus X plus X plus X, so equal N0 plus X. Since the reaction is at the gas state, now I will pass from number of moles to the pressure. And pay attention again, it's not allowed to convert the number of mole to concentration if the volume is not constant. And from the number of mole to the pressure, we have also to justify some conditions. So for a gas, PV equal nRT. And since R is constant, T in this problem is constant, we don't have any indication that the temperature is variable. So P is directly proportional, and V is constant. So P equal nRT divided by V. So P equal constant ratio times N. That means the pressure is directly proportional to the number of moles. So we can replace now, or we can transform the table of conversion from number of moles to the pressure, since the pressure is directly proportional to the number of moles in this problem. Why? Because the temperature and the volume are constant. As a conclusion, when you write the table of conversion, you write it as function of the number of moles. If the volume in the exercise is constant, you can transform N to the concentration. If the volume and the temperature in the exercise are constant, you can transform the table of conversion according to N to the table of conversion according to the pressure P. So construct the table of conversion as a function of the partial pressures now. I can transform the table from N to P. So at T equals 0, instead of N0, I can write P0. The pressure of CH4 the pressure of O0. So at time T, suppose we have X reacted from P0. So at time T, we have P0 minus X, X, and X. I add a table now. The total pressure at T equals 0 is P0. The number of moles total is equal to the sum of number of moles of all reactants and all pressures, of all reactants and all products. By the same way, for ideal gases in our problem, in our curriculum, all gases are assumed ideal. So for ideal gases, the total pressure is the sum of the pressures of reactant and the pressures of the product. I call these pressures the partial pressures. So the partial pressure of CH3CHO is P0 minus X. The partial pressure of CH4 is X. The partial pressure of CO is X. So P total equal P0 plus 0 plus 0 equal P0. P total equal at time t P0 minus X plus X plus X, so equal P0 plus X. Why I use P total? Why I add a column where we have P total? Since in the exercise, he asked us to find the rate, the integrated rate law as a function of P0 and as a function of P total. For this reason, I add a column of P total. What is the degree of conversion? The degree of conversion alpha, by definition, is equal to the quantity reacted divided by initial. So alpha is equal X divided by N0. This is by definition. The degree of conversion is equal to the quantity reacted per initial quantity. So alpha equal XO over N0. And in this problem, since I have a table of conversion according to the pressure, I can write alpha is equal X over the initial pressure. So X equal alpha P0. So this table of conversion at T equals 0, P0, 0, 0. At time T, according to the degree, this is according to the pressure that react to the pressure of the amount reacted from the initial. This is the table of conversion according to the degree of conversion alpha. So at T equal P0, at time T, we can put P0 minus alpha P0, X is alpha P0, X is alpha P0. So P total according to P initial and alpha is the following. P total at T equals 0 equal P0. At T equal P0 minus alpha P0 plus alpha P0. So P total equal P0 plus alpha P0. So till now, I transform the table of conversion according to pressure P0 and according to X, or in other words, in other form, I transform the table of conversion according to the pressure and the degree of conversion. Pay attention that these two tables are the same, are similar. So according to Dalton law, for ideal gases, the total pressure is the sum of the partial pressures. So P total equal P0 plus alpha P0 implies P total minus P0 equal alpha P0. Why I use to know alpha P0? In order to have the pressure according only to P0 and P total. Alpha is not given in this exercise. So P total minus P0 equal alpha P0. We replace alpha P0 by its value and we obtain the variation of the pressures as a function of P total and P0. So the pressure of CH3CHO at time T equal P0 minus alpha P0 equal P0 minus P total minus P0. so equal to P0 minus Pt. Now we have only the variation of the pressure as a function of the initial pressure P0 and the total pressure P total. The pressure of CH4 is equal P total minus P0. The pressure of CO is equal P total minus P0. For a second order reaction, this is given in the exercise 1 over concentration minus 1 over concentration initial equal KT, PV equal nRT. So P equal nRT divided by V, and N over V equal concentration. So P equal concentration times RT, and the concentration is equal to P divided by RT. This is the relation between the concentration and the pressure. I repeat, PV equal nRT. You can write P equal N over V times RT. N over V equal concentration. So P equal concentration RT, concentration equal P divided by RT. Now we can replace the concentration of CH3CHO at time T by its value P over RT. So 1 over the pressure of CH3CHO at time T divided by RT minus 1 over the pressure initial concentration, so we have the initial pressure, minus 1 over P of CH3CHO initial divided by RT equal KT. So RT divided by the pressure at time T minus RT divided by the pressure at T equals 0 equal KT. So 1 over pressure at time T minus 1 over pressure at time T equals 0 equal KT divided by RT. Previously, in the previous slide, we calculated P of CH3CHO at time T, which is equal to P0 minus Pt, minus what is the initial pressure of CH3CHO at T equals 0 is equal P0 equal KT divided by RT. So the relation of a second order reaction given in this exercise is transformed from concentration to pressures as a function of the initial pressure and the total pressure. The form is 1 over 2P0 minus 1 over Pt minus 1 over P0 equal KT divided by RT. So the correct answer, I don't know, I will see the correct answer is A. The correct answer is A. We have to remove this answer B. So the correct answer is therefore A.